Hey guys, I just got out of a meeting. I'll be back in about a minute and a half. I'll be right with you. Hang on. Okay, I'm back. Anybody got a question? No questions?
I have a question. I think Mitch was here first, but if he doesn't have anything, I can go. So I was wondering if you could go over an example involving the stack where like there's a function calling another function and they have like local variables and arguments and everything.
Um, let's see. We can concoct an example. Let's just do that. Why don't I just create a new file here? Uh, so let's see. We'll have a function and we'll pass in. Well, come to think of it, I've already got one out there. Why don't I just go get it? If I remember what it's called, it was called call 32.c, I think it was. So see this thing here? We've got this function f1, And here's the main function in the program. It's going to call function one, pass it these 6 parameters, and let's modify this a little so it won't optimize some things away when we compile it. Let's just create some integers. Let's create a bunch of integers, and then we'll, rather than passing these constants in there, I'll grab all this stuff. It's kind of slow today. My internet connection is really creeping along. Come on, respond. Oh, go back. What the hell? Oh, this is just ungodly slow for some reason. Get rid of that. All right. So let's do a and do a control wipe. Do it up. Control yank. Figure out why this is so slow. Let's get rid of this junk. Ah. Cancel. Get this out of the way. So why isn't this thing responding? Why is it so slow? Let's start killing stuff off. I think the idiot thing maybe launched a backup or something. It's slowing the computer down. Let's kill this thing off. Okay, so here we are back up there. And what I want to do is I want to take A and assign the 1 in there. And take B and assign the 2. C. 3 in there. And D. Put 4 in that. And then 5 will be E. And F will get 6. And then we'll call function 1 with A, B, C, D, F. Right? And so it adds all those together, right? And let's just add another one just for the hell of it. We'll add a G, and then in G, we'll pass the address of G, and then up here in this function, now what we'll have is a pointer to an int for the seventh parameter, right?
Mhm.
Buying that.
Yep.
And then in here, we'll say that um, G, this P2 guy, right? We'll dereference that pointer and stuff the result of that addition into that guy.
You mean P7?
Yeah, I'm sorry. P7. So that'll stuff it into this G back in the caller, right? Because we
Hmm.
passed the address in. So we can modify the thing that he passed into us. That's the way we modify something outside of the function, right?
Hmm.
And then we'll take I mean, this is really goofy, but we'll just say return what P7 has in it, right? So let's save that. We'll compile it, and I could compile it right out of Emacs, but I'll just show you the end that I would do here. GCC, and I want to compile this call 32.c thing, right? And it compiled it. And then if we run it, we're running a dot out because I didn't tell it where to put it, right? So it prints sum is 21, right?
Hmm.
But what you want to know about is you want to know about what's the assembly language look like, right?
Yep.
So do our capital S business and compile it. And so now we have this file called 32.s that we can look at. So we'll pop open an editor and look at the contents of that on my incredibly slow computer this afternoon. So get this out of the way. And now we'll make this bigger so we can see it. So here's our E code, and here's the assembly language. Any day now, it's going to render that picture across the internet. There it goes. So we go down to our main function and look at main. And you can ignore all this crud at the beginning of main. We can explain that later. But anyway, this part looks familiar to you, right? Push the base pointer, move the stack pointer to the base pointer.
Hmm.
Subtract 48 from the stack pointer. So what is that doing? That's creating space for these local variables to live in, right?
Okay.
So those local variables will be referenced as offsets, negative offsets from the base pointer, right? The base
Hmm.
pointer is pointing up at the top where the stack was pointing right after we saved off the base pointer, right? Then we move the stack pointer to the base pointer. So everything from the base pointer down, lower addresses, is this space that we've reserved for the local variables to live in, right?
Hmm.
And then here we're referencing those local variables. Ignore this crud here for now. So what is um, the $1 is that constant 1, right? And we're moving it 36 locations below the base pointer. So that's where the variable a lives, is 36 below the base pointer. Then 4 up, right, because they're integers, is where the the b lives. 4 up above that is where the c lives. 4 up above that is where the d lives, right? So those are all those variables that are being loaded with the 1, 2, 3, 4, 5, 6. But we also are going to pass the address of this g variable, right?
Mm-hmm.
So when we um, make the actual call, right, we're going to have the parameters being passed into the function that we're calling. So it's a 64-bit computer, right? Diane's silk dress cost $89, right? So the RDI is the first parameter we want to pass, which is the contents of the A variable. So we're grabbing 40 below the base pointer, putting it into RDI.
Isn't A 36 below the base pointer?
Hang on a sec. Yeah. So 36 is going into EAX, and then we're going to do what? We're pushing the RDI, moving EAX to EDI. So that's how it actually got in there to pass it, and then we did the call. So this business here, right, where it puts 40 into the RDI and then pushes the RDI on the stack, that's how we're passing the G, right? Does that make sense? So G lives at 40 below the base pointer, right? We had to get
Mm-hmm.
its address. You see this load effective address? Getting the address of what's 40 locations below where the base pointer points and putting that in RDI. Then it pushed it onto the stack to pass that parameter because we have 7 parameters. You can only fit 6 into the registers, right?
Okay.
Diane silk dress cost $89. You only get 6 registers to pass parameters. So we got a 7th one, so we got to pass it through the stack, right?
Right.
So this is where it's actually passing that second parameter, getting the address of where G is and shoving that address onto the stack. And then this EAX where they temporarily put um, the A one, I guess it is, gets loaded into the DI. So there's A getting sent in, right?
Mm-hmm.
I mean, there's other ways it could have concocted to do that. But once we get there, we've got all our parameters set up. 6 of them are in registers. The 7th one is sitting on the stack, right? And then we call function 1. So all that, you buying all that?
Yeah. So if we had more than 7 parameters, it would just keep pushing them onto the
Keep
stack.
stuffing them on the stack. You got no other choice at that point, right?
Mm-hmm.
So then when we get back up into the function 1 up here, right? He pushes the base pointer, moves the stack pointer to the base pointer, and now he's going to get the parameters. Diane silk dress cost $89. The registers that those parameters came in. And this, if we turn on further optimizations, you wouldn't see it doing this. But what he's doing is he's saving off all of those parameters into his activation record, right? Just saving a copy of them, right?
Okay.
But you could if you turn optimizations on in the compiler, you get smart enough to not do that, right?
Right.
And if you look at -4, that's where he put the first thing, the P1, right? And he's putting that in EDX, and then he goes and gets -8. That's where he put the second one, and he moves that EX and EDX, then he adds the two together, right? Goes and gets the third one, puts it in EAX, and then he adds EX to EDX as his running total, right? And he's getting the next one, and he's adding it in, getting the next one, adding it in, right? That all makes sense doing this addition here, right?
Mhm.
So you add all that crud up, and then you want to um, store it back in the local variable G in the main program, right? That came in, we got his address there, right? For the
Mhm.
seventh one. So the seventh one is going to be where? What's going on here? Yeah. 16 past the base pointer into RAX. That's the sum that we're going to be returning. Okay, yeah. So then here is the running total kept getting put into EDX, right? And 24 was the last of the sixth parameter. That's P6, right? So this is taking the P6, adding it to getting it in EX, and then adding that to his running total. So now in EDX, he's got the sum of all those first six parameters that came in, right?
Right.
And now he's going to say, okay, go 16 locations above positive offset where the base pointer is pointing and put that in RAX. So I ask you, what is that doing? Well, remember when we pushed the address of this G guy?
Mhm.
There he is getting it off the stack, right? Because if you go positive offsets from the base pointer, you're going back up into the caller's record on the stack, right?
Mhm.
Negative ones live in your activation record, right? So that's getting that address of the variable that we passed in and putting it in RAX, right?
Uh-huh.
So now he's doing this business to take the um, where that address points into memory, right? And pick it up and put it into the EAX register, right? That's this
Mhm.
business here, right?
Right.
You're going to return it by putting it into the EAX register. Well, the value you're going to return is the value that's stuffed in there, right?
Mhm.
Right. And here you see where he saved off after he added all of them up, right? This is where he saved off the sum is in the EDX, right? He went 16 back and got that address, right?
Mhm.
He moved what was at that address into RAX. So now he's got the address of the variable. So here he's putting the sum into where that address points back in the main program. Does that make sense?
Right.
That's this business right there, right?
So it's sort of like setting G to the sum.
Yeah, he's got the sum computed in the EDX register. He went into the stack 16 back to get the address that we just got passed for this parameter, right? We passed in an address of a variable to him. So he takes that address that he's plucking off the stack there, puts it in RAX, and now he says, take that sum that I computed and stuff it into the address pointed to by that address that you passed to me, right? So that actually is doing the assignment into this P7, which is this G variable that we passed in the address of, right?
Mhm.
That's how he's actually from this function reaching over into main and shoving that into that variable, right? because we
So
handed him the address of it.
so if we like printed out G instead of sum, it would still print out 21, right?
Yeah, when we get back here, we could print G and it would say 21, right?
Mm-hmm.
And because all we're doing here is picking up the value, I mean, that's this part here. He's going back to get the address, puts it in there, which is kind of silly because he already had it. And if he hadn't clobbered it, you know, but the optimizer might get rid of some of that, right? But
Right.
anyway, now you got the RAX guy, which is the same address of the G variable. And then he says, put that, the value pointed to by that address, right, into EAX. This is how you return something from a function, leave it in the EAX register.
Mm-hmm.
So that's the value of the function getting returned, which is getting assigned into this sum variable. And we printed it out, but we could print as well. I really can't type today.
I think I get how it's storing it in G and it's also storing what it's stored in G into the return, and then that's putting in
Yeah,
the sum.
right. It's the way that I wrote the little silly thing. It returns the sum as the value, but it also stuffs the sum back in that G variable, right?
Mm-hmm.
So here, if we just print out what G is, right? And then we'll compile it. And what we want to compile is call 32.c. Yes, save it for me. So he compiled it, and now we want to run it. So run that. And so you see, well, I didn't change the name. I should have said ZG here, right? Right. So there you see, it's the same thing, right?
Mm-hmm.
So does that make sense how the parameters are getting passed? But once you get more than 6 of them, that's all you have in the register passing convention, right? So any excess ones you got to pass on the stack.
So back in the function code and assembly, um, right at the beginning, it's putting everything in lower addresses than the base pointer. So it's like going below the base pointer.
Being these saves here.
Yeah.
Yeah, it's just kind of if this function one had turned around and called some other function, then we would have to use these registers to pass the parameters to that other function.
Mm-hmm.
So this is saving them off in case we needed to use them to call somebody else, right?
Right.
But if you turn more optimizations on in the compiler, he will notice, oh, this is a leaf function. He doesn't ever call anybody, right?
So it wouldn't actually
So
do
it
that if it
wouldn't
was
save all that
optimizing.
crap because he knows he doesn't need to reuse these registers to have parameters he's passing to another function, right?
So when it's saving those off, that's kind of saving them off above the stack, right?
No, that's saving them on the stack. So the current activation record is the space between where the base pointer is pointing and where the stack pointer is pointing, right?
Uh huh.
Now, he didn't actually in this move the stack pointer down to create an actual honest to goodness activation record, the distance between the SP and the VP, but he's using what we call the red zone, right?
Uh huh.
Below where the base pointer is pointing to save off his local variables, right? We saw an instance of that before. So he's kind of behaving like a what you would expect for a leaf procedure where he's choosing this red zone and not moving the stack pointer. But then he doesn't need to save them off anyway because he's not going to call anybody. So he's kind of halfway doing the optimization you would do for a leaf procedure and halfway not. But if we
Okay.
flip more optimizations on, we'll probably see this chunk go away, right? Let me make an
S-
experiment, try it. Let's just come back over here and then we'll compile it again. And I'll change the compile command to say like, oh, optimize level 2 or something and see if he'll get rid of it. Oh, but I gotta see the assembly language. So I don't really care about what the code does. So let me do it again. So let's uh, yeah. So this one I need to get rid of this. And then over here I want to compile it, but I want to do my dash S business, right? Because we want to see what the assembly language looks like. So then we'll come in here. We'll get the thing again, the new version of it. And any day now, it will actually show us what's in there. See if you optimize that away. Yeah, it's gone. Plus, see, he didn't save them off. So now he's doing add these two together, add those two together, add those two together, right?
mhm.
And now, so he's got Diane silk dress. Oh, it's adding EDI to EDX and EDX to ECX. So he's got summed it all up into ECX, right? He's got 1, 2, 3, 4 of them summed up in there. And then he goes 8 back off of the stack pointer, not 16 because he didn't even bother to save the base pointer, right?
Oh yeah.
So he's only going 8 back rather than 16, right?
Hmm.
And then he gets that address, sticks it in RDX, and now he says, what's the effective address of R8 added to RCX? So that's just a trick to add what's in the parameter for 8, R8, to what's in the parameter for the CX, which he hasn't summed up here. And then he puts that in EAX. So that's the other two. So he's got all 6 of them now, right? He got 1, 2, 3, 4 of them summed up there. And then he took that one. No, that's the 5th one. Now he needs the 6th one is R9. So that's the 6th one. So now he's got them all summed up, right?
In
And why
EAX.
he chose to do load effective address to add those two together rather than just a regular add instruction, who the hell knows? The compilers, have their own little logic they're going through that's inscrutable sometimes. But in any event, in EAX now he has the sum of all 6 of them. And so now he's going to move that to what RDX points at, because that's the address that he plucked off the stack that points back to the G that lives over in the main guy, right? So there he is stuffing it into the G, but he's already got the result in EAX, which is the return. So he's out of here, right?
Okay.
So when you turn more optimizations on, you'll see him do less, wasteful stuff. He didn't even use any local space below his, he didn't even move the base pointer and do all that crap, right?
Hmm.
Just left the stack pointer pointing where it was when you entered the function and based that getting that other parameter off the stack pointer. Eight
So,
back because it's 8 back because you're hopping over the return address, right?
uh-huh.
Right. That makes sense.
Yeah. So in so
But he got smarter when you turned it on. As an 03 level, he may even get smarter. He may figure out that he doesn't even need to do these, and he'll just take the constants and stick 21 in there. So, you know,
I see that sometimes it's just not moving the stack pointer and stuff. Is it still like in theory the base pointer and stack pointer are like
a honest to God, righteous activation record frame for the local currently executing function, right? In the 32-bit convention is the space between the base pointer and the stack pointer.
mhm.
In the full optimized version for the 64-bit, it doesn't use the base pointer for anything. It just bases everything off the stack pointer.
Okay.
So what it'll do is it'll, like if you wanted a real activation record where you needed space for local variables to live, you'd see them dropping the stack pointer down by subtracting something from it. And then when he references in the local function, the local variables, they would then be positive offsets back up in the stack to get to those local variables, right?
Okay.
If it's a leaf procedure, though, you'll see him doing stuff like this, where he just leaves the stack pointer where it was. And if he had to access local variables, he would just use the negative offsets, the space below where the stack pointer is pointing, and wouldn't have to even move the stack pointer. So when he returns, it's where it needs to be to do the return, right?
Okay.
So he's got all those kind of optimized or not optimized kind of things based on whether it's a actually needs space for local variables to live, don't really need any space. I'm just doing a bunch of crap in these registers, right?
Hmm.
So in this one, he didn't really need any local variables, right?
Right.
We could force him to do it by coming over here and doing this trick. We could come in here and we could declare an integer array of 10 integers or some crap, right? And then to force him not to optimize that away, right? We'll say volatile, which is just a trick we're using saying, Mr. Compiler, every time I touch this array, you stuff something back into memory where that guy lives. So this is
Mhm.
going to force him to allocate space for it and do these assignments we're about to do. So if I didn't put that volatile there, the optimizer would look at this going, well, why do I need to do all this shit? You're not going to use it for anything. I'm just not going to emit any code for it at all, right?
Mhm.
Because you just dump a bunch of crap in there, and then when you return from the function, it just disappears. You never did anything with it. So it would just optimize all that out of existence, right? But this is a
Right.
way of trying to force him to say, yeah, really create some space for that in your local activation record and really stuff these things into it when I say to, right? That's what that volatile is doing. So
Mhm.
we can force him to show us making a local activation record, right? By doing this kind of crap. So we'll do a control X S, save it, Alt X, up arrow, compile, and we'll do the same, compile, just hit return with O2. Now we got to reload this guy though to see it. Up arrow. While that's loading, I'll just do a less so we can see it faster. So let's see what's going on. Oh, crap. See what's going on in function one here. Yeah. See, he's actually creating an activation record by subtracting 56 from the stack pointer, right? That's creating space to hold that array of 10 integers, right?
Okay.
Right. That local variable that we created.
Right.
So we forced him to do that with that volatile statement. So he actually really created a real honest to God activation record for the currently executing function by dropping the stack pointer down, right? And here we forced him to actually access it, stuff things into memory. So we're going to see here move RAX. That's something else. Don't worry about that. I'll explain that later in the course. This is the first thing you need to worry about. This is the first parameter, the P1, right?
Mm-hmm.
And we're putting it where the stack pointer points. And then we're adding, so the P2 guy needs to go 4 locations above that, right? So let's see what's going on here. He's saving off. This is the P1 going into A sub 0, right? Right where the stack pointer is pointing.
Mm-hmm.
And then that is doing the add. That's doing this one. This is taking the second parameter and that's putting it in A sub 1. See, he's 4 above where that guy lives, right?
Mm-hmm.
A is going from where the stack pointer is pointing back toward higher addresses, right? This is A sub 0. This is A sub 1, right?
Right.
So those are actual local variables living in my activation record that I created with this. Give me some space, right?
Mm-hmm.
And then when you get ready to leave, of course, you got to shrink it back, which you see right here. He's adding 56 back to the stack pointer just before you do the return, because now you're sitting underneath where the return address is, right?
Mm-hmm.
So, if you create an activation record, then you got to throw it away right before you return, right?
Right.
So we forced him to do that with this CRUD here. And so why is it 56 locations that he saved off? Well, the amount of space we needed was 4 times 10. So that's 40 bytes. But there's a rule, and it has to do with alignment constraints, right?
Mm-hmm.
That um, the place, like if we turned around and called another function, right, then we would add a return address would be 8 bytes would get stuffed onto the stack. So that would make 8 plus 56, which is 64, which is divisible by 8, right?
Mm-hmm.
So he always, when you land in a function, has to arrange it so that the stack pointer is pointing at something divisible by 8 so that all these things that we stuff into the local variables on the stack will be able to obey alignment constraints, right?
Mm-hmm.
Does that make sense?
Yeah.
So that's where he got this 56 from. It's the first number that's bigger than 40 um, 8, right? So it's 64 minus 8 is what it is, how he came up with that computation. So he will, if we had called somebody else, then that 64 bytes, if it was true that when we got here, the stack pointer was pointing at something divisible by 8, then when we did a call with somebody else, this 56 plus 8 would guarantee that the new guy's stack pointer, when he comes into existence, is pointing at a location divisible by 8. And then when you access things, you can arrange for the alignment constraints to be adhered to because you know that the stack starts at a location divisible by 8. It all has to fit together, right?
Hmm.
So it's kind of a bunch of little details, but it's very logical. And this is defining what's called the calling convention for the C language for this particular architecture. So it's a cross between how are the compilers going to emit code for this particular language on this particular architecture. And then some of the alignment conventions are even OS specific about how the things in that environment want to do it versus some other environment or whatever. But if you had another language like Pascal or Ada or whatever, the calling conventions could be a different set of conventions, right? For how it uses the architecture to create the semantics of the high level language function call, right? So it's a language slash architecture, and then in alignments or somewhat slash OS environment conventions.
Okay.
So you understand how the stack discipline works now?
Yes, I think so. Yeah, that's helped a lot.
Yeah, it's pretty cool, right? So
Hmm.
when you write a compiler, you have to arrange to spit all this crap out, that plays this game when this function gets called, right?
All right, I think that's all the stuff I had questions about.
So call by value, and then everything in C is called by value, but the value you pass in can be an address. And then you have to manually explicitly dereference it. Whereas in other languages, you could write something like var int in front of that, which tells the compiler this is going to be an address passed in here. And then when you use P7, he would automatically dereference it for you, right? Because it has pass by reference as well as pass by value. But C only has pass by value, so you have to manually pass in the address as the value and then manually dereference it.
Mhm. Well, thanks for your help.
All right, good luck. Well, I'm gonna have to head off to another meeting. It's 3:00. Do you have any more, one last question maybe, or not? No questions? Okay, well, I'm gonna shut her down then, head to that other meeting. Bye-bye.